the slides.
Okay, sure. Okay, everyone. Thank you for joining us, and I'm very pleased to introduce Bruce Blackadar from University of Nevada in Reno, and he's speaking on Hilbert spaces without countable axiom of choice. Bruce.
Okay, yeah, thank you, and thank you for inviting me. I'm sorry you can't see my face, but I think maybe the slides are the important thing. So this is joint work with Ilyas Farah and Asaf Karagila, and we've been looking at Hilbert spaces and operators without the countable axiom of choice. Whoop. Oh, now I'm okay. Oh, what's going on here? There we go. Okay, so some of you probably think it's silly to try to do functional analysis without the AC. And a year ago, I would have agreed with you, and I still mostly agree. I always thought you really couldn't do much of anything without the axiom of choice. But it turns out that's not true. I got into this project, and as research projects often go, it went in unexpected directions and turned out to be much more interesting than I expected, at least as an intellectual exercise. And I've also learned a lot about set theory in this. I know much more set theory than I did a year ago, although I'm still far from an expert. Fortunately, I have two co-authors who are experts. So things get rather strange, but I think you'll find that they're interesting. We're going to look at Hilbert spaces and operators without any form of choice, and we're especially going to look at Hilbert spaces whose dimension is finite, in a sense incompatible with even the countable AC. So first, let me remind you what the axiom of choice says. This is one version of it. If you have a collection of non-empty sets, then there's a choice function that picks an element out of each set. Or another way of saying that is, if you have a collection of non-empty sets, then their Cartesian product is non-empty, because the elements of the Cartesian product are by definition just the choice functions. And then the countable axiom of choice, which we abbreviate CC, is the same thing, but where you just have a sequence of sets. So the index set is the natural numbers. There are lots of other versions of choice. There's dependent choice, the Boolean prime ideal theorem, and many others. And they more or less fit in between these two, but not exactly. I won't be talking about the other ones. We don't have the axiom of choice, we can't use many of the usual tools that we take for granted in functional analysis. Things like Zorn's lemma, Tikhonov's theorem, the Hahn-Banach theorem, the Baire category theorem. These all require some form of choice. And if you don't have countable choice, you can't even prove things like the sequential criteria for continuity and closure in metric spaces, or even that a countable union of countable sets is countable. And we'll see a dramatic counterexample to that in a little while. But one important thing is that we can still make finitely many choices without any additional choice assumptions besides the normal Zermelo-Fraenkel axioms. So what we have to do is set aside almost everything we think we know about Hilbert spaces, operators, C-star algebras, and more generally Banach spaces. And we have to prove or reprove everything from scratch. You shouldn't forget what you know, because that's a good guide to what you should try to prove. And some things will work identically with the same proofs. Some things are still true, but they require different proofs. And some things are just no longer true. Okay, so we're particularly going to be interested in looking at what are called Dedekind finite sets. So a set is X is Dedekind finite if every injective function from X to X is surjective. Or in other words, X is not equipotent with any proper subset of itself. and otherwise X is Dedekind infinite. And you can make the same definitions for cardinals. So of course, any finite set is Dedekind finite, and any subset of a Dedekind finite set is Dedekind finite. We'll use the abbreviation DF to mean infinite and Dedekind finite. So the key characterization of this concept is that a set is Dedekind infinite if and only if it has a countably infinite subset, or in other words, a sequence of distinct elements. If you have the countable axiom of choice, then every infinite set contains a countably infinite subset. So it's Dedekind infinite. So you can't have any DF sets. DF sets are incompatible with the countable choice. But if you don't assume the countable choice, there are models of ZF that have Dedekind finite sets. And if you have one DF cardinal, then you have a lot of them, because you can take a Dedekind finite set and remove a finite number of elements out of it, and you get a set of strictly smaller cardinality. And so you can actually get a strictly decreasing sequence of DF cardinals, which contradicts the well-ordering principle. And you can even get a set of DF cardinals order isomorphic to the real numbers. And in some models of ZF, you can get 2 to the aleph naught mutually incomparable DF cardinals. Without the axiom of choice, cardinals aren't necessarily comparable. And in some models of ZF, you can even have that every set is an image or quotient of a DF set. So the collection of DF cardinals is not a set. So we have a huge zoo of things here if we don't have countable choice. Excuse me. At least in some models of ZF. There are some stronger flavors of Dedekind finiteness. So first, some notation. The absolute value of X we'll use to denote the cardinality of the set X. P of X, the power set of X, is the set of all subsets of X. And fin X is the set of all finite subsets of X. So fin X is a subset of P of X. And we have this these inequalities between the cardinalities. So if one of these sets is DF, then the sets to the left are also DF. We'll say a set X is co-infinite if fin X is Dedekind finite, which just says that X does not have a sequence of distinct finite subsets. And X is power Dedekind finite if P of X is Dedekind finite, which means that X does not have a sequence of distinct subsets. And we'll use the abbreviations CF and PF to mean infinite and co-infinite, or infinite and power Dedekind finite. And by the way, this is as far as you can go, PF, because if you have any infinite set, then the power set of fin X, and so therefore also the power set of X, is always Dedekind infinite, because you can take for any n, you can take the collection of n element subsets of X, and that gives you a sequence of distinct elements of this P of fin X. So I already pointed this out about what PF and CF mean, but there's an interesting set theory fact, which is actually surprisingly tricky to prove. That is that if X is a set that has a sequence of distinct subsets, then it has a sequence of pairwise disjoint non-empty subsets. The converse of this is, of course, trivial, but this is pretty tricky to prove. If the subsets are finite, it's easy. You can just take some successive differences, but it's very subtle to prove this if the subsets are not finite. And if you get bored in the rest of this talk You might try to see if you can figure out a proof of this. If you haven't seen it before and you figure out a proof, I'll be impressed. This theorem is due to Kuratowski. So as a result, if X is an infinite set, then X is PF if and only if it does not have a sequence of pairwise disjoint non-empty subsets. And it's CF if and only if it does not have a sequence of pairwise disjoint non-empty finite subsets. Okay, here's an interesting type of DF set. A set is a Russell set. Russell is Bertrand Russell, who was the first one to look at these. Or a set of Russell socks if it's DF, but it's a union of a sequence of pairwise disjoint two-element sets. So the way to think of this is these two-element subsets are called pairs of socks. So you have a sequence of pairs of socks, but there's no way to pick out which sock is the left sock and which sock is the right sock. And you can't do that globally. You can do it out of any individual pair or any finite number of pairs, but not out of all the pairs at once. So a Russell set is DF, but it's obviously not CF. There's a sequence of disjoint non-empty subset finite subsets. There are interesting things about Russell socks. One of the things is you have a set of Russell socks and you add another pair of socks. Well, now you have more socks in the sense that you have the set of socks you have is a strictly larger cardinality, but you still have the same number of pairs of socks. Bizarre. Okay, here's another maybe even stranger kind of DF set. A set X is amorphous if it's infinite, but it can't be written as a disjoint union of two infinite subsets. Or in other words, every subset is either finite or cofinite. So an amorphous set is PF. And any infinite subset of an amorphous set is amorphous. And as an indication of how strange these sets are, an amorphous set cannot be totally ordered. It's a good exercise, not very hard, to show that if you have an infinite totally ordered set, you can cut it somewhere in the middle into two disjoint infinite subsets. So these sets are very strange. Here's a somewhat related idea, but turns out a little different. We say that an infinite set X is rigid if every permutation of X moves only finitely many elements of the set. We're interested in permutations because if you have a permutation of the set X, it naturally defines a unitary operator on L2 of X. And that operator is a finite rank perturbation of the identity if and only if the permutation moves only finitely many elements. And then we say that the set X is strongly rigid if whenever you partition it into non-empty subsets, all but finitely many of the subsets are singletons. And so a strongly rigid set is rigid because if you have a permutation, you can divide X into the orbits. You have some implications between the different flavors here. Strongly rigid seems to be similar to amorphous, but neither thing implies the other. But we'll say a set is strongly amorphous if it's amorphous and strongly rigid. These are the most finite kinds of infinite sets you could imagine, and rather curious sets. So how do we know sets like these exist? Well, in 1922, Frankel constructed a model of ZF with atoms. So it's not quite ZF set theory, which has a strongly amorphous set. And then in the 60s, it was shown that this can be converted into a strongly amorphous set in a model of ZF. And then Cohen, in his famous work in the early 60s on the independence of the axiom of choice and the continuum hypothesis, constructed a model of ZF in which the real numbers has a CF subset. And then there have been more recent models giving Russell sets and these other various things. So these occur in different models of ZF, but it turns out you can combine all the models via what are called transfer theorems to give a single model of ZF that gives all the flavors of DF sets that we've talked about. So you really can get sets like this, but they have to be models in which the countable axiom of choice doesn't hold. Okay, so that's the end of our little whirlwind excursion into set theory. But we'll use these different kinds of sets as we go on. So now let's talk about Hilbert spaces. First thing we have to do is get the right notion of completeness. Usual notion of completeness of a metric space is that every Cauchy sequence converges. And that's what we'll call Cauchy completeness. But it turns out without countable choice, this is not really the appropriate notion of completeness for a metric space. So instead, we use what we call sigma completeness. So a metric space is sigma complete if whenever you have a decreasing sequence of closed subsets whose diameters approach zero, the intersection is non-empty. And of course, it's necessarily a singleton. And it turns out that this is equivalent to X being complete in the uniform structure defined by the metric. And it's also equivalent to X, the metric space being absolutely closed in the obvious sense. And it implies Cauchy completeness, but it's not equivalent without the countable choice. If you do have countable choice, then these conditions are all equivalent. Because if you have countable choice and you have this decreasing sequence AN, you can just pick an element out of each AN. And because the diameters of the ANs go to zero, that sequence has to be a Cauchy sequence. Okay. So we define a Hilbert space to be a complex inner product space, which is sigma complete. We operator algebra people like to work on complex spaces, but everything I do works equally well and maybe even slightly easier for real Hilbert spaces. So real or complex is not important here. And more generally, we would define a Banach space to be a normed vector space, which is sigma complete. Well, the most important fundamental property of a Hilbert space is the so-called closest vector property. That if you have a non-empty closed convex subset of your Hilbert space and any vector in the Hilbert space, there's a unique closest vector in the convex set. The usual proof of this uses Cauchy sequences. You take a sequence of vectors in C whose distances from the C approach the minimum. And then you prove a lemma from the parallelogram law that basically says that the Hilbert space is uniformly convex. And that lemma implies then that sequence is a Cauchy sequence, and the limit of it is the closest vector. Well, you can't do that argument if you don't have countable choice. But there's an alternate argument using sigma completeness. And let me just go through this to illustrate how you use sigma completeness. And this proof doesn't use any kind of choice. So let's let R be the distance from C to the convex set. And for each n, you let AN be the intersection of C with the closed ball of radius R plus 1 over n around C. So you get a decreasing sequence of closed convex subsets in H. The same lemma about uniform convexity shows that the diameters of these ANs go to zero. And so by sigma completeness, the intersection is a singleton, which is your closest vector. And this proof, by the way, works equally well in any uniformly convex Banach space, as long as you take sigma completeness as in your definition of Banach space. Okay, well then you get all of the standard properties that Hilbert spaces have, basic properties. Any closed subspace of a Hilbert space has an orthogonal complement, and there's an orthogonal projection onto the subspace. You get the Riesz representation theorem that every bounded linear functional on a Hilbert space is inner product with a fixed vector. Every bounded operator on a Hilbert space has an adjoint, or more generally, any bounded sesquilinear form on a Hilbert space is defined by an operator. But one important thing is that all of these things can fail if your inner product space is only Cauchy complete. There are examples there. Okay, well, of course, we all know that one of the nice things about Hilbert spaces is they have orthonormal bases. If you have the axiom of choice, then you have this standard result that any Hilbert space has an orthonormal basis. Any orthonormal set can be expanded to an orthonormal basis, and any two orthonormal bases have the same cardinality, which is just saying that orthogonal dimension is well defined. And you need the axiom of choice to prove this theorem for general Hilbert spaces, but for separable Hilbert spaces, you don't need any kind of choice. You just do Gram-Schmidt. So we usually think that Hilbert spaces aren't very interesting because they all look pretty much the same, right? They're the same up to size. Well, without the AC, all the parts of this theorem can fail. Now, you might think that this is being a big negative problem, but we view this more positively, that what this means to us is that Hilbert spaces are much more varied and interesting without the axiom of choice. There are even infinite dimensional Hilbert spaces that are so different that every bounded operator between them has finite rank. So we really get some weird Hilbert spaces here. Now, the Hilbert spaces that do have orthonormal bases, you can nicely describe as L2 spaces. So here's the definition of L2 of a set X. And what do we mean by the sum over X? Well, we take it to mean the integral with respect to counting measure. So if you have a non-negative function on X, then it's the supremum of the sum is just the supremum of the sums over finite subsets of X. So for any function from X to the complex numbers, this sum is well defined. And if it's finite, then it's an L2 function. And in the usual way, you can show that this is a vector space, and it has a natural inner product defined in the usual way. And you can prove that it's sigma complete. So it's a Hilbert space. The completeness proof is just a variation of the usual completeness proof that we're all familiar with, modified a little the way we modified the proof of the closest vector property to work with sigma completeness. Okay, so we have this collection of nice Hilbert spaces, and L2 of X, of course, has a natural orthonormal basis indexed by X, just the characteristic functions of the elements of X. And conversely, if you have a Hilbert space that has an orthonormal basis indexed by the set X, then H is isometrically isomorphic to L2 of X. That's pretty easy to see. So these L2 of X's are universal models for Hilbert spaces with orthonormal bases. We're going to be particularly interested in L2 of X when X is DF. And turns out there are some surprises here. So the first thing to note is that if X is DF, then L2 of X is, excuse me, is not separable because you can't approximate all the basis vectors closely within, say, less than 1 over square root of 2 by a countable set. We're conditioned to thinking of non-separable Hilbert spaces as being bigger than separable ones, but that's not really accurate in this setting. A non-separable Hilbert space is not necessarily either larger or smaller than a separable one. It's just different. Okay, so here's the first interesting example to look at. Let's take X to be a set of Russell socks. So X is a union of a disjoint union of a sequence of 2 element sets, Xn, and it's df. So if you take script Xn to be the span of Xn in L2 of X, then these are mutually orthogonal 2-dimensional subspaces, which span the whole space. And each one has a distinguished orthonormal basis. But the orthonormal basis is unordered. You can't say which is the first and which is the second basis vector in each of these 2-dimensional subspaces. But you can still take the sum of the 2 basis vectors. You don't have to know which one is first to do that. And you let eta sub n be the sum, and then you normalize it to make a unit vector, and you get an orthonormal sequence in L2 of X. So let's call the closed span of the eta sub n. So let's call that Y. And so that's isomorphic to L2 of the natural numbers, which is what we usually just call little L2. And for future reference, let's write Z for the orthogonal complement of Y. And we'll come back and talk about Z in a minute. So what we get is we can show that even if X is df, L2 of X can contain an orthonormal sequence. And even more is true. If you take L2 of the disjoint union of X and the natural numbers, well, it's just isomorphic to the direct sum of these 2 Hilbert spaces. And you split up the L2 of X into Y and Z, and you get 2 copies of L2 of N, which you combine into 1 copy. So L2 of N is isomorphic to the direct sum of 2 copies of itself. And so you end up with that this L2 space is isomorphic to L2 of X. So what that means is that L2 of X has an orthonormal basis indexed, of course, by X, which is a df set, but it also has another orthonormal basis that's indexed by this disjoint union, which is not a Dedekind finite set. So orthogonal dimension is very much not well defined. We don't have a notion of orthogonal dimension here. We can view these subspaces Y and Z in another way, because you have a permutation of X that just interchanges the 2 socks in each pair, or the 2 basis vectors in each of these 2-dimensional subspaces. And that defines a self-adjoint unitary operator on L2 of X. The square view is the identity. And Y and Z are just the +1 and -1 eigenspaces of this unitary. Okay, so let's look at this subspace Z. This is quite an interesting Hilbert space. It's spanned by the differences of the basis vectors in each of the Xn's. So it's a closed span of a sequence of 1-dimensional subspaces. But the problem is that the difference of the basis vectors is only well defined up to sign. You have to decide which one is the first and which is the second. And you can't do that globally. You can't make a global choice of sign. So you can't make an orthonormal sequence out of these vectors. Even though you've got this sequence of 1-dimensional subspaces, you can't pick you can't pick unit vectors in each one. And in fact, Z is not separable, because if Z was separable, since Y is separable, then you'd get that L2 of X is separable. And we know that that's not true. Actually, it seems quite plausible that Z doesn't have an orthonormal basis, and we think this is probably true. This is claimed by Brunner and some co-authors in a paper. They refer to a proof in another paper by Brunner. We haven't been able to follow that proof, and we're a little skeptical because they also claim that this implies some other things about Z which are not true. So we're skeptical that this is something that's known, but we think it's probably is true. But we can jazz things up a little bit into a set of super Russell socks, where the pairs of socks are not indexed by the natural numbers, but they're indexed by a strongly amorphous set. And in the same way, we get a self-adjoint unitary U, and the eigenspaces Y and Z. And we can show that in this setting, this subspace Z does not have an orthonormal basis. And in fact, it's the opposite extreme. Every orthonormal set in Z is finite. So there's an example of a infinite dimensional Hilbert space in which every orthonormal set is finite, and there's no orthonormal basis. Okay, now let's look at what happens if if our set X is CF. So here we get some curious properties. The first thing is that every vector in L2 of X has finite support. So in other words, this orthonormal basis is actually a Hamel basis. This is pretty easy to see, because if you have a vector, a square summable function, and you take any epsilon, the set of coefficients that are bigger than epsilon in absolute value has to be a finite set, because the function is square summable. And so if you take epsilon to be 1 over n, you get a sequence of finite subsets of X whose union is the support of the vector. But if X is CF, then any increasing sequence of finite subsets of X has to stabilize at some point. And by the same proof, not only does any individual vector have finite support, but every sequence of vectors in L2 of X has finite common support. So any sequence of vectors in L2 of X have to all lie in some finite dimensional subspace of X. So in particular, you can't have an orthonormal sequence in L2 of X. And just as a sort of an aside, this shows that the closed unit ball of L2 of X is a sigma complete metric space, which is sequentially compact, but it's not compact because it's not totally bounded. You can also get an interesting, another interesting example. If you take a CF set, which is not PF, so that means you can write it as a disjoint union of a countable number of non-empty subsets. They're not finite subsets, but they're subsets. You can define a bounded operator on L2 of X just by taking it to be 1 over n times the identity on the nth subspace. And this is injective, but it's actually also surjective because every vector has finite support. But the inverse is not bounded. And that gives you a simple counterexample to the open mapping theorem and the closed graph theorem. And if you look at truncations of the inverse, you get a counterexample to the uniform boundedness theorem. And of course, the usual proofs of these theorems use some version of the bare category theorem. And it's known that these theorems are actually essentially equivalent to countable choice. Okay, so let's look a little bit more at bounded operators. if you look at the set of bounded operators on a Hilbert space, there's still a lot of the properties that we normally work with persist. Operators have support projections, you have polar decomposition, you have continuous and Borel functional calculus of self-adjoint elements. There's a version of the spectral theorem. But behavior can be dramatically different if you take L2 of X, your Hilbert space, to be L2 of X, where X is sufficiently DF. So here's a very interesting fact. We think it's very interesting, has some nice consequences. If X is a CF set and T is a bounded operator on L2 of X, then the X actually decomposes into finite subsets, which are invariant under T. So your T has many finite dimensional invariant subspaces. It takes some work to prove this theorem. But here is a quick consequence of this, is that if X is CF, then B of L2 of X is stably finite. It contains no non-unitary isometries, and no matrix algebra over it does either. And if X is strongly amorphous, this implies that every bounded operator on X is a finite rank permutation of a scalar. So there's a nice reformulation of this. If X is a strongly amorphous set and you take H to be L2 of X, then it's an infinite dimensional Hilbert space, and every closed subspace of H has either finite dimension or finite codimension. This is because if you just look at the projection P onto the subspace, then P has to be a finite rank perturbation of a scalar, which means that either P or 1 minus P has finite rank. So you get that this H is a, you could call it a hereditarily indecomposable Hilbert space. Well, if you have the axiom of choice, you have to work pretty hard to get a hereditarily indecomposable Banach space. And it's actually not even quite as hereditarily indecomposable as this Hilbert space is, because as I learned, every infinite, if you have the axiom of choice, every infinite dimensional Banach space has an infinite dimensional closed subspace that has infinite codimensions. I asked this question on Overflow, and you guys answered it, and I showed my ignorance about Schauder bases in that discussion. I'm not an expert on Banach spaces. And by the way, we think that this closed can be eliminated from this statement, and that is just a statement about vector spaces. What you have is a vector space, complex vector space, with a Hamel basis indexed by a strongly amorphous set. We think every subspace ought to have either finite dimension or finite codimension, but we haven't been able to prove that. Okay, so let's look at spectrum of operators. The spectrum still has the usual properties that we're familiar with. You don't need any choice to prove properties about the spectrum of an operator, or elements of unital Banach algebras, that is, complex Banach algebras. The spectrum is always a non-empty compact subset of the plane. You have the spectral radius formula, etc. If X is a PF set and T is a bounded operator on L2 of X, it turns out that the spectrum of T has to be finite. And furthermore, every element of the spectrum is actually an eigenvalue. So these operators behave very much like operators just on finite dimensional spaces. Again, it takes a little work to prove this theorem. On the other hand, if X is not power Dedekind finite, then every separable compact subset of C occurs as the spectrum of a normal operator on L2 of X. And I should mention that if you don't have countable choice, you can't prove that compact subsets of the plane are separable. They're separate, they're second countable, but yeah, we don't know that they're separable. But there are a lot of separable compact subsets of the plane, the closure of any bounded sequence, for example. Okay, so now let's talk about compact operators. And the first thing is we have to decide what's the right definition of a compact operator. Because under the axiom of choice, there are several well-known equivalent conditions for being compact, and you have to pick one of them as your definition. If you don't have the AC, these conditions are not equivalent anymore. So we have to decide which one we should take. And we decided on this definition as the best one. And I think it's maybe the best one even if you assume the AC. We say that an operator on a Hilbert space is compact if the image of every bounded set is totally bounded. This definition is good because you can easily prove from this the basic properties that the compact operators K of H have without using any form of choice. You can show that K of H is a closed two-sided ideal in B of H, and it's the closure of the finite rank operators. And I should also point out that if H is infinite dimensional, then K of H is a proper ideal in B of H, because the identity operator is not compact, because the unit ball is not totally bounded. Then you can pretty easily show that if X is CF, then every compact operator on L2 of X actually has finite rank. So now let's look at the Calkin algebra. And this is what got me into this subject to begin with, because I thought the Calkin algebra might be a potential source of examples of or counterexamples to an old open question in C-star algebra theory about whether every quasi-trace on a C-star algebra is a trace. We actually haven't made any progress on that question, and I'm pessimistic that that we will. But the project, our research project, went in a different direction. So the Calkin algebra of a Hilbert space H is just the quotient C-star algebra B of H mod K of H, which is defined whenever H is an infinite dimensional Hilbert space. So it's well known that if H is infinite dimensional and separable, then Q of H is simple and purely infinite. But for other Hilbert spaces, it can be very different. It can even can be stably finite even. And we have some equivalent conditions that B of H and Q of H are stably finite if and only if H does not contain an orthonormal sequence. And if H has a orthonormal basis, it's L2 of X for a set X, these are equivalent to X being CF. So if X is strongly amorphous, then from that result about every operator being finite rank perturbation of the identity, you get that the Calkin algebra of L2 of X is just the complex numbers, just one dimensional. And you can get the n by n matrices as the Calkin algebra of another set. The Calkin algebra is not necessarily simple. In fact, it can be a direct sum of two C-star algebras. And there's a simple example. And we even have an example where the Calkin algebra is commutative and non-separable. It's isomorphic to the quotient of L infinity modulo C0 for some infinite set Y. So it can be very far from being simple. We suspect that it's rarely, if ever, separable if it's infinite dimensional. And we also think it's rarely simple if H is non-separable, just like what happens for under AC for non-separable Hilbert spaces. Should work similarly, but maybe in a little more complicated way, that the ideal structure should be related to the partially ordered set of infinite cardinals that are infinitely dominated by the cardinality of the set X. But if you have a Hilbert space that doesn't have an orthonormal basis, we don't have any clear idea of what Q of H looks like, or B of H for that matter. Well, we came up with some Hilbert space versions of the flavors of being DF, and these look potentially interesting. If you have an infinite dimensional Hilbert space, H, we could say that H is HDF if it's not isometric to a proper subspace of itself. So this is the Hilbert space version of being DF. And so this just says that there are no proper isometries in B of H. H is HCF if it doesn't have a sequence of mutually orthogonal non-zero finite dimensional subspaces. It's HPF if it doesn't have a sequence of mutually orthogonal non-zero closed subspaces. And it's Hilbert amorphous if every closed subspace has either finite dimension or finite codimension. So these are the analogs of being CF, PF, or amorphous. And we have some implications here. HDF turns out not to be very interesting, but the other ones I think are, we think are potentially quite interesting. HDF is just equivalent to being, oh, sorry, I have to say something else first. These notions are notions for Hilbert spaces, but we can actually get notions for sets also. So we get some things that apparently set theorists have never considered before, because you have to work through Hilbert spaces to get them, but they're set theoretic concepts. We say that the set X is HDF, or for the other ones, if L2 of X is HDF. So HDF is not very interesting. It's just equivalent to being CF. But the other ones we think are new. They're potentially new flavors of Dedekind finiteness that maybe set theorists are going to be interested in. Along with this, we also have potentially new pre-order and equivalence relation on cardinals. So if X and Y are sets, we say that the cardinal of Y is curly less than or equal to the cardinal of X if L2 of X contains a subspace isometric to L2 of Y, which is just saying that L2 of X contains an orthonormal set of cardinality cardinal of Y. And we say that the two cardinals are equivalent if the L2 of X is isometric to L2 of Y. And we have a Schroeder-Bernstein theorem, which says that two cardinals are equivalent if each one is curly less than or equal to the other. The proof of this is just a straightforward variation of the proof of the usual Schroeder-Bernstein theorem of set theory. This ordering is a much weaker and equivalent pre-ordering than the usual partial order on cardinals. For example, if X is a set of Russell socks, then Aleph naught is curly less than or equal to the cardinal of X, even though this is a DF cardinal. And this DF cardinal of X, is equivalent to this non-DF cardinal here. So we've only scratched the surface of the properties of these pre-orders and equivalence relations, but these are things that may turn out to be interesting in set theory. And so we have some applications of Hilbert spaces to set theory here, possibly. And I'll just conclude by mentioning that this is a project that we will be thinking about in the future to try to compute the K-theory and non-stable K-theory of B of H and Q of H for these kinds of Hilbert spaces we've been considering. This could be complicated to answer, and the answers will probably depend on what model of ZF we're working in. So we don't know what the potential answer is here, but it's something that we're going to think about in the future. We also have some results about C-star algebras, and those are going to go into another paper. But I think I'm out of time, so I'm going to stop here, and I'll just put up a little table here that shows the implications between the different kinds of DF-ness that we've been considering. The ones in the upper left are the new ones we've introduced, and there could possibly be some more arrows in or out of those. But other than that, there are no more arrows that can be added to this diagram. So I'll quit here. Thank you.
All right, thank you so much, Bruce. That was a very, very nice talk. Are there any questions or comments? Are you able to see the chat? There's a just ignore it. Yeah, okay. Just ignore it. Okay.
I have to get back. Let me see here. This is
okay. Any other math questions? Okay.
Oh, here's the chat. Okay.
Okay.
I don't see any messages on chat.
Sorry, Benjamin, hello, I am Ahmed. I sent you a question for Bruce. Huh?
You have a...
Yeah, I think we can ignore that. Sorry about that.
Okay, yeah, I don't see anything on chat, but of course I couldn't get my picture up, so that doesn't mean there isn't something there. But if you have a question, go ahead and ask me. I may not be able to answer it, but maybe Elias can answer it.
Actually, I was just about to ask a question to mention it. Did you ever check what happens with the K-theory, like both periodicity theorem and all things like that? Does any of that require axiom of choice?
Well, I haven't really looked carefully at that. I don't think there's a problem with that, but things are can be a little tricky. We lots of things, as we know, use some version of the AC without some hidden version, and I keep finding things that where somebody's used the AC, or at least the countable AC, and not even realized it. So yeah, we should really look at that more carefully to see what parts of K-theory work and what don't. I think most of it works, if not all. I'm sure there's some things that don't work, but yeah.
Thanks.
Any others?
There is a question in chat now.
I'm not sure if you want to go there. Yeah. Okay.
Oh.
It might be spam.
Oh, now I see something on chat.
I took a quick glance. It seemed like a spam of some sort.
Well, actually, I mean, I should just mention that the usual way that the number system, including the real numbers, are constructed doesn't use any version of the of choice, and so you can construct the real numbers within any in the usual way within any model of ZF. They have somewhat different properties depending on the model, but you can do the constructions And you can also prove, basic things like the Bolzano-Weierstrass theorem, the Heine-Borel theorem, without any version of choice.
Okay, thank you. All right, so if there is no other questions or comments, thank you so much again, Bruce. I'll stop recording here.